Hi guys. Today we're going to finish off our moon information, or our moon lessons, just by talking about tides. Tides can be a really tricky concept because there's a lot of physics involved with the way they actually work. I'm just going to show you a quick clip in a second, and I'll show you how complicated it can be. But the big thing that you need to know is that every day there are changes in the elevation of the ocean, which are caused by primarily the force of gravity by the moon. Okay, so tides are primarily caused by the gravitational attraction of the Earth and the moon system. There is some effect by the sun, but the sun is much further away, so it has less of an actual gravitational attraction on the Earth's oceans. Now, every day the Earth rotates once, as we already know. It rotates around in a complete circle in 24 hours. And every day, the Earth spins under what we see here, a water bulge, this bulge in the ocean, a tidal bulge in the ocean, which is always located on where the side where the moon is and the opposite side away from the moon. This bulge is created by a squeezing of the Earth's oceans due to some tidal attraction, which is a little bit complicated, like I said. And I'm just going to play a quick clip of how complicated that can be right here.
The key is to look at the tidal acceleration of objects that are not on the Earth-Moon line. For instance, a block at this location is going to be pulled this way by the moon, but of course the whole Earth is pulled that way by the moon, chasing after the block. So relative to the Earth's surface, the block's tidal acceleration is almost radially inward, in other words, down. In fact, if we map out the tidal acceleration vectors that you'd see at different points on Earth's surface, they look like this. As you can see, tidal forces only act like anti-gravity if you're right on the Earth-Moon line. At most places, those vectors are largely tangent to Earth's surface, which would push water sideways. So I think you can start to see what's happening here. The ocean isn't being lifted or stretched. Instead, thanks to the cumulative sideways traction everywhere else, it's being squeezed toward the Earth-Moon line and piling up there. Basically, the moon is turning the entire ocean into a planet-sized hydraulic pump.
Okay, so big takeaway from that, I know that's kind of complicated, is the fact that we have a bulge in the Earth's oceans, and the Earth rotates underneath of that bulge. And so it's one given location, we're going to rotate into this tidal bulge over here where the ocean is higher, and then we're going to rotate over into this section again at some point during the day. So every day, because the Earth spins around once, we're going to experience a high tide twice and a low tide twice. And the best way to explain that is in this interesting animation right here.
Now we can see why, when the Earth rotates through 24 hours, it goes through 2 high tides and 2 low tides.
Now, given that video, if we have 2 high tides per day and 2 low tides per day, they are approximately 12 hours apart. Okay, so if you look at a graph like this kind of graphs out a typical location of high tide and low tide. The ocean level at some point during the day is going to be relatively lower than average. Okay, and what that would look like on a beach, you might be able to go to a beach and you could walk out way out into the ocean. You might see all these rocks and shells and maybe some critters that didn't get out into the ocean before the tide went out. And then at some point during the day, probably about 6 hours later, the ocean level is going to start to come back up again. And now the water level comes back up, and you aren't going to be able to walk out to that location anymore. So now we're experiencing high tide about 6 hours after. And then about 6 hours later, it drops down to a low tide again. And then 6 hours later, it's back up to a high tide again. And then back to low, and over and over and over again. And you can see on this graph, really, really simply, this is a very cyclical, predictable graph. You can know exactly when the high tide is going to happen after this, because this has been happening in a regular pattern throughout all of our records. Okay, now notice the amount of time between the high tides. It's about 12 hours. Okay, a little bit more than that technically. And the time between low tides is about 12 hours as well. All right, I just want to show you there are some places where there are really extreme high and low tides. This is actually a picture of the Bay of Fundy, which is up in Nova Scotia, so just to the northeast of us. They have a tide of low and high of a difference of around 20 to 25 feet. And so you can go out during low tide and walk out there, but high tide 6 hours later is going to come in and the water level is going to be about 20 feet above your head. The Bay of Fundy is an interesting shape. The water kind of gets funneled in there. And so because of that funneling, we have this really extreme rise in the tides. And when you get further up into the bay, up into this area like Truro up here, it's a really, really extreme tide. And you actually see the water moving up the bay. It's called a tidal bore. It's like a tidal, they call it a tidal wave, really, and just pushes its way up through this river into this location up in here. Now, because it's so extreme, you really have to keep track of the tidal charts. And I want to show you this really quick, cool time lapse of the Bay of Fundy rising and falling. And I'll show that right here. Okay, so tides are caused again by the gravitational attraction of the Earth and its oceans and the moon. Okay, however, we have to recognize the fact that the moon goes around in a complete cycle all the way around the Earth in 29 and a half days. Okay, and because of this revolution of the moon around the Earth, we also have some noticeable changes during some of the major phases of the moon, the new moon and the full moon. Okay, and that's due to the way everything's lining up. So let's take a look at this system here. Remember, I said earlier that the moon has the primary effect on tides. The sun does as well, but not as much. Now, it is possible for this to all work together. So during a new moon, when the Earth, the moon, and the sun are all lined up in a straight line like this, now we have the gravitational attraction of the moon as well as the sun kind of pulling together, almost like a tug of war. Okay. And when they pull together, they actually greatly exaggerate this tidal bulge in the Earth's ocean. So it makes the high tides much higher than normal. So once during the month, when there's a new moon, we have an extra large high tide. Okay. Now, there's also times in this cycle when the moon is located over here and the sun is located over here at 90-degree angle to each other. And now they're kind of counteracting each other, they're counterbalancing each other, and there's not as much of an effect on the tides. There's not an extreme tide. It's more like average all day, not a big high tide, not a big low tide. Over here, the full moon is over here. Okay, now we have a nice straight line again, and now we're playing tug of war with the moon on one side, the sun on the other side, and now we're going to have an extreme tide again. And then back to third quarter, now we're counterbalancing that 90-degree angle. Okay, so there are two different types of tides throughout the month. There's what we call a spring tide, and this is when we have the greatest tidal range, when we have a big jump in our graph. And that's due to the alignment of the Earth and the moon and the sun all in a straight line. And that's going to happen during the new moon and the full moon, so twice a month. Okay, it also happens that we can have this counterbalancing act, and that's called a very fun word, a Neap Tide. So now we have the sun and the moon at a right angle to each other, and due to the fact that they're kind of acting against each other, there's less of a daily change in this tidal bulge. There's a little bit more due to the moon because it's closer, but there's not an extreme tide here. They're not pulling together, and therefore it's not as noticeable of a change. And so twice a month this happens during the first and the third quarter moons. Okay, and you can kind of see that in this picture here. This picture here shows the spring tides, again, all lined up in a straight line during the new moon and the full moon. And then the neap tide is going to happen when they're counterbalancing each other. And this is called a solar tide and a lunar tide. The lunar tide is much higher because it's closer. The moon is a lot closer than the sun is. Okay, so this is a calendar that kind of shows the difference between the spring and the neap tides throughout a month. As you can see here, this is a whole month that's displayed on the x-axis, the full moon, and then the last quarter moon, and then the new moon, and then the first quarter moon. And remember, it's about a week between these 7 days, approximately between each one of these. And remember, this whole entire cycle is 29.5 days long. Now notice every day it's high tide, low tide, every day. But I'd also like you to notice the difference between the high and the low tide here when the full moon is happening and when the new moon is happening, okay? And this is called a spring tide. We have an extreme leap, like a springboard, right? Big from high to low. It's a really big jump. During the last quarter moon and the first quarter moon, there's not as much of a noticeable difference because the sun and the moon are kind of counterbalancing each other. So I just want to show you that throughout a whole month. Okay, so let's do a few region-style questions. This one was related to tides in Montauk, New York. Montauk is actually at the very tip of Long Island, so way out into the Atlantic Ocean. So they experience tides. Now you'll notice here the y-axis of the graph is showing you the height above average low tide level, and then the x-axis is time. So it says what's the height above average low tide level at noon on January 24th. So you just have to find where noon is. That's right here. Go up the graph until you hit the line, and that's right around, it's above 1, below 2. So it's somewhere in between 1 and 2. It looks like it's closer to 2, so probably around 1.6. And so the answer to this question is number 2, 1.6 feet. Okay, here's 2 more questions that are very, very common with tides. It says these changes in water levels at Montauk can be best described as what? Well, remember, any graph that looks like this, up and down and up and down and up and down, that's a cyclical graph. And remember, pretty much hand in hand with that, because it's cyclical, it's very predictable. So the answer to this question is number 1. Okay? Number 38 here, what causes the water level variation pattern shown by the graphs? In other words, what causes tides? Has to do with 2 things. Number 1 has to do with the fact that the Earth's oceans are gravitationally attracted to the moon. So it has to do with the pull of the moon, as well as the fact that the Earth is spinning every day, so rotating. So it's number 4 for this question. Okay, so that's it. If you guys have any questions about tides, don't hesitate to ask.